Okay, let's start then. So today is an extra session. This is like a concluding session. So we shall discuss today bits in like we shall summarize whatever we studied in this course throughout the 12 weeks and what are the learnings from the course. Okay. And if you guys have any doubt, you can ask me. So today I haven't kept numerical problems. I think I have kept one or two, and I didn't also get time. But if you have any particular numerical problem that you want to be discussed, or you find any problem later, also you can mail me. I can answer. Or if you today also if you want any problem to be discussed, we can discuss. So I shall briefly summarize today, and then yeah. So today will be the last session. So so in this course, this is basics of power electronics. So we started from the very basic, which is switches, right? So when we talk about power electronics, we will have to talk about switches. So there are different kind of switches. First, we talked about ideal switches. Then different types of semiconductor devices that we studied. It can be uncontrolled, it can be controlled. So what are the categories that we saw? And we also studied their static and dynamic characteristics, right? So we among them there was diode, then MOSFET, IGBT, BJT, all these things we studied, right? And then we also studied about rectifiers, single phase rectifier, as well as there are also three phase rectifiers, but mainly we talked about single phase rectifiers. And then we studied about the rectifier with capacitive filter. What are the advantages? Then if we connect a capacitive filter, there is a problem, that is the problem of inrush current. So how can we protect the devices from the inrush current? That we also saw there were different types of protection circuits, protection elements basically. Then there was linear regulators, right? And finally, we talked about switched mode DC-DC converters. So from this point onwards, the actual like the power electronic part started, the switched mode DC-DC converter. So the most basic kind of converters were buck converter, boost converter, and buck boost converter. So buck converter basically steps down the input voltage, and we get a step down version of the input voltage. Boost converter, from the name itself, you know that boost converter basically steps up the input voltage, and we get a higher voltage than the input voltage. And buck boost converter can perform both the actions. It can step down also, it can also step up the voltage. And finally, we have the isolated DC-DC converters, where we talked about the buck-derived isolated converter, which is the forward converter. We talked about the buck-boost derived isolated converter, which is also called the flyback converter. And among the other things, we studied some topics based on the design of the circuits. So primarily, we studied the design of magnetic components, which includes the inductor and transformer, high frequency transformer that we use in the isolated DC-DC converters. Then we talked about the driver circuits of BJT and MOSFET. Then and in the last week, we studied the closed loop control, right? We studied about the closed loop control and also pulse width modulation a bit, sinusoidal pulse width modulation, right? So yeah, I shall discuss like all the topics. I will just touch upon briefly. If you have any query, just ask me, interrupt me and ask me, or you can also write in the chat the question. Okay, whatever you like. So yeah. So first of all, the ideal switch. What it's very important, right? To understand the ideal switch. If you don't understand the ideal switch properties, you will not be able to understand the actual switch properties, the practical switches. So practical switches are nothing but ideal switches, like switches, but with some non-idealities, right? But so for ideal switch, what are the properties? The properties are like this. So when the ideal switch is in off condition, when this is when the ideal switch is off, right? In that case, it can block infinite amount of voltage, and it there will be no leakage current. The current will be absolutely zero, and it can block any amount of voltage. Whatever, no matter whatever voltage you apply, it can block it. Similarly, when it is in on condition, when it is on, then it can carry any amount of current. It can carry infinite current in both the directions, right? And the voltage drop across the switch will be zero. There will be no voltage drop, right? So the characteristic will be something like this. All the four quadrants will be the operating area, because it can block voltage in any direction, in this polarity also, in the opposite polarity also, and it can also carry current in both the directions. So the its operating region will be both for all the four quadrants. But obviously, practically, we don't get any such device unless unless we connect them in some series or parallel combination. We can't get the operating region like this in all the four quadrants, right? With a single device, we can't get this kind of operating region. And next up, we have this. We studied in detail diode, right? Which is an uncontrolled device. We studied the static characteristic of the diode and also the dynamic characteristic of the diode. What is the dynamic characteristic? The dynamic characteristic of any switch means the time, the voltage, current, all this information with respect to time. Right, the waveforms. That are the dynamic waveforms. Yeah, one more thing is, for ideal switch, the turn on and turn off occur like instantaneously. But for practical switches, this diode or MOSFET or IGBT or BJT, they take finite amount of time to turn on and also finite amount of time to turn off. You can't instantaneously turn them off or turn them on, right? So basically for an ideal switch, the characteristic turn on characteristic will be like this. So its voltage, suppose it is turning on, right? So its current will rise like this instantaneously, and the voltage will also fall if this is the current during turn on. Then voltage will also drop like instantaneously. There is no time taken. So you can see there is no overlap between the voltage and the current, right? That's why there is no switching loss. But practically, there will be some finite slope. The current will not rise like this, the current will rise like this with some slope, right? With some slope. And the voltage will also fall with some slope, right? With some slope. So there will be some overlap. When there is current also, there is voltage also. So we get some switching loss in practical devices, right? So this is uncontrolled device diode. So you can't control when it will turn on and when it will turn off. Based on the circuit condition, it may turn on and it may turn off. You don't have any control over it. But for BJT or for MOSFET or IGBT or for other control devices, you have some control. So BJT and MOSFET, so they are fully controlled switches. You can control the turn on also, you can control the turn off also. Whenever you want, you can turn them on. Whenever you want, you may also turn them off, right? Based on their drivers. So for BJT, you will have to provide some base current over here to make this on. If you make the base current zero, it will go to the cutoff state, cutoff region. And for MOSFET, you will have to provide some gate to source voltage. So if this is the source terminal, this is the drain terminal, and this is the gate terminal. So you will have to provide gate to source voltage greater than its threshold voltage. Then only it will be in it will be on, right? And if you withdraw the pulses, then it will be off. So this is a current control device. This is a voltage control device because we will have to give some gate to source voltage. But here in case of BJT, you will have to provide some base current. Where, unless and until the base current is flowing, your BJT will be on. Okay. So these are some different types of switches that we studied. Yeah, so here I included some a model of the MOSFET. So this we didn't discuss. I don't know whether this is in the scope of the syllabus, but just for the sake of completeness, I included this. So basically for a MOSFET, uh, we already know that there is this capacitor in the gate to source junction, right? There is this CGS capacitor. But there are two other capacitors, they are parasitic capacitors, mind you. These are not physical capacitors. If you just buy a MOSFET, you will not see this kind of capacitors like this. They are internal. They appear like they come because of the structure of the MOSFET, right? So they are parasitic capacitors. There is CGS, there is CDS, which is across drain and source, and there is CGD, which is across drain and gate, right? And these capacitors are not constant. So if you just see any data sheet of a MOSFET, you will see that the kind of like this. So initially the capacitor will be very large. Suppose uh, uh, before that they are called CISS, COSS and CRSS. In datasheet you will not see these values CGD, CGS or CDS. In datasheet you will see these three values. CISS, COSS and CRSS. CISS is called the input capacitance, right? What is the input capacitance? So if you input capacitance means that is the capacitance seen from the input side, right? So if you want to find out the equivalent capacitance, you can short the output like this, and then you will see that CGD and CGS they come in parallel, right? Because if you are shorting the output, the drain to source, if you are shorting, then CGD and CGS comes in parallel, right? Because this is one common point and this is another common point. That's why the input capacitance is the summation of CGD and CGS. Okay. Then comes the output capacitance. So you can find it similar way. What you will have to do, you will have to short the output in that case, right? If you short the gate and source terminals just for the sake of analysis, like not actually, just for the sake of analysis, if you just short it, then you will find CGD and CDS, they come in parallel, right? So this is CGD plus CDS. And what is CRSS? This is reverse transfer capacitance. This is called. This is CGD, this one. Because why this is transfer capacitance? Because there is this input term also, gate, which is the input, and there is drain, which is the output. So that's why this is transfer capacitance. Okay. So CRSS value is usually very small, and CISS is the largest one. CISS is quite large. Okay. But usually, like if you see, and these capacitance values change over the voltage. If so, if you see, the switch will have some certain, suppose 800 volt or 1200 volt, some breakdown voltage. So along the voltage, the capacitance values will decrease, and then like something like this, maybe initially it is very high and then it settles to a low value like this, CISS suppose. Okay. And they are usually in log scale, they give it. You can see any MOSFET data sheet, and you will see that the you can check the values, right? CISS is the largest one, and then COSS and CRSS is the smallest one. Okay. So these are the parasitic capacitances, and they will be specified at a particular voltage, at a particular VDS, right? At a particular VDS, they will be specified. Okay. So because they are not constant, they vary with the voltage. So that's why at a particular VDS, they will specify these values. Yeah. So we also talked about the thermal aspect. What is the thermal aspect? So how will you choose a heat sink? So in practical switches, there are two types of losses. There is conduction loss and there is switching loss, right? And in switching loss also, you will get turn on loss and turn off loss, right? So if your device junction temperature becomes too high, then the device will get damaged, right? The device will get damaged. So what you need to do is you need to protect the device. How will you protect it? You will have to connect some material with the device so that the heat can be dissipated. That is what is heat sink. Heat sink helps to dissipate the heat and maintain the junction temperature, right? So that it doesn't increase too much, so that your device gets damaged. Just a minute. Yeah, so for the sake of understanding and for the ease of understanding, we make an equivalent model of the thermal circuit, right? So we are habituated with resistances, then current sources, voltage sources. So that's why we uh, make the circuit based on these elements. Okay. So suppose your power loss in the device is P, so that we model as similar to a current source. And the RTH, the thermal resistance from junction to ambient. That is R thermal junction to ambient. That is modeled as a electrical resistance, right? And then you have these two nodes. In this node, your temperature is Tj, which is the junction temperature. And in this node, the temperature is the ambient temperature. And in between, you have this resistance. So if this is a current source, then obviously the current will flow, right? Current will flow, and this is equivalent to the potential difference. The difference of temperature, we can think it as a potential difference. So now the circuit is very simple. So what is resistance? Resistance is voltage difference by the current. So power is equivalent to current here, and the temperature difference is equal to the voltage difference. So that's why this formula comes. Okay. Now, in the data sheet, you will find that they specify what is the maximum allowable junction temperature. So if you know the maximum allowable junction temperature, then you know Tj. Tj is known. And you also know the ambient temperature. So these two quantities are known. And analytically, you can find out what will be the power loss in the device. Analytically, you can find out, right? So in that case, you can find out R thermal junction to ambient. What will be your required R thermal junction to ambient? And this junction to ambient resistance is the summation of junction to case resistance and case to ambient resistance. Okay. So there will be two resistances. This one will be, there is one resistance and there will be another resistance. So the first one, R thermal junction to case, RJC, R theta JC. What is this junction to case? The junction to case is specified in the device datasheet. This value is already specified. So you can know this value. And this value you also know, right? This value you also know. And this is also known. So you can find out case to ambient. Case to ambient you can find out. So what will this resistance consists of? So case to ambient means, so suppose this is your device. I am showing you the cross section, suppose. So suppose this is your device, right? So this is the drain tap that is connected to the heat sink. So between the heat sink and the drain tap, suppose this is an MOSFET, right? So this is shouldered like this. So, so this is suppose the drain tap, and here in between the heatsink and the device drain tap, there will be some thermal interface material. Okay, some thermal interface material, and after that there will be the heatsink. Okay, usually we do like this only. Okay, because if you are using some metallic heatsink, suppose aluminium or some other metal, then if you are and you will attach multiple devices to a heatsink, then the drains will get shorted, right? Because that if you directly connect the drain terminals to the heatsink of multiple devices, so they will get short via this heatsink. That's why we apply this thermal interface material, that is also called TIM material. The abbreviation is called TIM material. Okay, so this TIM material will have some thermal conductivity, and based on that we can find out what will be the thermal resistance, and then there will be the thermal resistance of the heat sink. So this total thing we call it case to ambient, right? Case to ambient resistance. So yeah, so whenever you will choose the heat sink, you will have to choose this value carefully, so that your the junction temperature can be maintained within a certain limit. Okay. So after that we discussed about rectifiers. So what is a rectifier? The rectifier is a circuit which converts AC signals to DC signals. It converts AC quantities to DC quantities. So over here, if you have a single phase AC voltage like this, and you just connect a diode here, then you will get a voltage like this at the output. So this lighter one is the AC voltage at the input, and this black one is the rectified output voltage. Okay, that you will get across this load. So you see, this voltage is not, it is not changing polarity. It is DC. It is DC, and then for some time it is remaining zero, but it is not changing polarity, right? So that's why this is a rectified voltage. But we have some pulsation here. This is not a proper DC like this. There is some pulsation, but still it is a DC voltage. Okay. The simplest rectifier. This is also called half wave rectifier because you are only getting one half. The another half you are getting zero because the diode can't conduct. The diode becomes reverse biased. That is why this is called a half wave rectifier. We also have a full wave rectifier where you will have these four diodes like this. Okay. Yeah. So you have these four diodes like this. Okay. So for one half cycle, these two diagonal diodes conduct, and for the next half cycle, these two diodes will conduct. And that's how you get both the halves. This is the positive half, this is the negative half. Okay. So here obviously the average value will be more than the previous one because now you are getting two humps like this instead of just one. Okay. And how to determine which diodes will conduct when? So there is a process. So there are two configurations. So we already discussed this previously, but I will just repeat. So basically there is common cathode configuration and there is common, sorry. So there is common cathode configuration and there is common anode configuration. So common cathode configuration means the cathodes of the two diodes, they are at the same potential, right? They are shorted. And common anode is the anodes are shorted, right? The anodes are at the same potential. So for common cathode configuration, so if you look at these two diodes, these upside diodes, they are in common cathode configuration, right? Their cathodes are connected, these two diodes. So for this kind of configuration, the diode with the highest anode potential will conduct. So whichever's anode, this among this one and this one, whichever anode will have the higher potential, that diode will conduct. Okay. And for a common anode configuration like this, it is the opposite. Whichever's cathode will have the most negative lowest potential, that diode will conduct. Okay. So that's how you can determine which diode will conduct and which diode will not conduct. After that, we saw that as we have this kind of pulsation in the rectified voltage, and we want to have a kind of DC steep DC voltage like this. Okay, so that's why we connected one filter, capacitive filter. Okay, so this filter we connected here. What is the advantage? The advantage is this. So the advantage is the capacitor will not allow to fall the voltage this much. The capacitor will maintain the voltage to almost a constant value. Okay. So I haven't showed the waveform, but here I can show. Right. So basically, the steady state waveform will look like this. So suppose the output voltage is becoming like this. So in this portion, when the input voltage is just above the capacitor output voltage, then only the current will get drawn from the input and till this maximum point, and then again the capacitor will provide the load current. Okay. So the voltage will look like this. So you see, compared to this voltage is much better, right? This voltage is almost steady DC with some very small amount of ripple, right? But there is a problem. What is the problem? The problem is we face an issue that is called the inrush current issue. What happens is basically you have the AC voltage over here and you have this uncharged capacitor. When you are starting the circuit, the capacitor is not charged, so there is no voltage across the capacitor here. Now, if you just connect, so these diodes are basically just switches, nothing else, and you don't have any control over the diodes also. So if you just connect this voltage via a switch to the capacitor will draw momentarily, it will draw a huge current, which may damage the diodes. Okay, which will damage the diodes if the current rating exceeds. Because there is no impedance in the circuit to limit the current. There is just these two voltage sources and very small amount of resistance. So that resistance will be some due to some source resistance and some forward resistance, some dynamic resistance of these diodes. That's it, which is very small. So the impedance is very small. What will be the current? The current will be VI, this voltage, minus VC divided by Z, the impedance of the circuit, which is very small. So the initial current is too high. So we will have to do something to limit this current. So there are various solutions that we discussed. Okay. There are various solutions. So there are these resistive solutions where you can just connect a resistor in series. So here you can connect a series resistance like this. You can also connect a thermistor whose resistance changes with temperature. So as the temperature increases, its resistance falls. Okay. So they are also called NTC, negative temperature coefficient. Okay. So you can also use thermistors and transformers. Transformer based solutions are also there where you will get isolation also and you will get protection against the inrush current also. Okay. And there are also relay based solutions that we discussed. You can check the PDFs, the presentation of those weeks. So I have not discussed in detail the solutions, but yeah, so here there are the two cases where the case one shows that here we are starting the circuit at the zero crossing. We are starting the circuit at zero crossing, means that when this AC voltage is zero, at its zero position, then we are closing this switch. In that case, the inrush current will be lower because this voltage is zero or very close to zero. So that's why there will be not much current. But in the worst case is what? When the input voltage is at its peak, at that time, if you close the switch, then it will be very huge current. It will be very large. So this current will definitely damage your circuit components. Okay. So that's why a protection circuit we need to use. Okay, for limiting the inrush current. So this is the first cycle. First two cycles, maybe you will get this kind of current. Then the current will, in the steady state, this much current will not get drawn. But at the first cycle or first few cycles, the current will be very large. Okay. So this is another issue that we discussed with the rectifiers. So next we discussed the linear regulators, right? We discussed the linear regulators. Now, if we have AC voltage, then the diode bridge rectifier, we don't have any control over this output voltage because this is just diodes and a capacitive filter. You can't control the diode. So this is not a controlled switch. So you don't have any control over the regulated you can't get a regulated output. Even if the output voltage fluctuates due to some disturbance in the input side, you don't have any way to maintain it at a constant value. So you will have to put something in between the unregulated output voltage, and to get the regulated output in between you will have to put something. So these DC-DC linear regulators are there. And we also studied about switched mode converters. You can also use switched mode converters to control. So first we discussed the linear regulators, but they are not very efficient. That's why they are not used in high power applications. We use switched mode converters. Okay. So yeah. So there is this shunt regulator. Okay. There is this shunt regulator where if you want to just regulate this voltage, so we use a Zener diode, right? We use a Zener diode, and this series resistance is there with the source. What is the property of a Zener diode? So the Zener diode operates in the breakdown region. So for normal diode, the operation is like this. There will be one knee voltage or a cutoff voltage, and afterwards there is this rise in current. And here there is very small leakage current, after that the breakdown region. For normal diode, we don't go to this breakdown region because the diode will be damaged. But for Zener diode, this is the region that you need to operate. The breakdown region is the region that you will operate. Okay. So here the this portion is like this, and then there is like this. So you see, so if this is your current axis, and this is your voltage axis. So even though in the y-axis your current is increasing and increasing, but voltage is more or less constant. Voltage is almost constant, right? So irrespective of the current through the diode, you can maintain a constant voltage. That's why in the regulator, the Zener diode is used. Okay. Yeah, so these are some of the equations that we studied. What will be the maximum current? What could be the minimum current? Okay, so these things we studied. And then we also studied the series regulator, right? We studied the series regulator. So in that, unlike the shunt regulator, here you will have to put a series element, and that series element, the impedance of the series element will vary. Suppose this is a resistor, but with variable resistance. You can implement some control strategy so that this resistance varies based on your output requirement. So if your output voltage increases, if it increases from a reference value, then this resistance value will also increase, so that the drop across the resistance increases, right? In that case, the voltage here will decrease because they are connected in series. So the drop across RS, if this increases, then it will definitely reduce, right? Because this voltage is constant. So like that. And similarly, if it reduces, then you will also reduce the resistance value, so that again you can get the same output voltage, right? So this is the main operating principle. And how to implement this? You can implement it like this. Okay. You can implement it with the help of BJTs and Zener diodes. So here you have this output voltage, and here you have a resistive divider like this. And from this point you tap it and take the output voltage, the fraction of the output voltage. this is the base drive of this BJT, right? This is the base drive of this BJT. And over here you have this Zener diode, so that you can have the reference value. So this Zener diode, across the Zener diode, you get your reference value. Okay. Now you see here the potential is VI, right? So some current flows through RB, and this current gets divided in two parts. One through the base drive of this BJT, another here in the collector. So as soon as this voltage, output voltage, increases from its actual value, from the reference value, then the base drive also increases. The base drive of Q2 increases. As the base drive of Q2 increases, so the beta IB also increases, right? The collector current of Q2 also increases as the base current increases. Now this current is constant, right? This current is same. Now this is drawing more current. So the current through this BJT, the base drive through this BJT decreases. Okay, as the base drive through this BJT decreases, then the BJT will go towards the cutoff region, and it will start to block more and more voltage. As it will draw more, like block more and more voltage, then the voltage across the load will reduce, right? Because Pi is the summation of voltage drop across Q1 and across the load. So Vi is the summation of VQ1 and V output, VQ1 and V output. So, if VQ1 increases, then VO this has to decrease, right? To maintain the summation equal to Vi. That's how this series regulator can regulate the output voltage. Okay, so at this point, I will take a small break of 5 minutes. So meanwhile, if you have any question after the break, you can ask me, or otherwise we can continue this discussion. Okay.
Okay, ma'am.
Okay. 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 Okay, so let's resume the discussion. So yeah, so we discussed about series regulators, shunt regulators, and series regulators. So basically,
Yeah.
yes,
And how this reference voltage is getting created from the load.
how this?
Reference voltage is getting created from the load now.
No, reference voltage we don't create from the load. The load voltage is the one that you need to regulate, right? So your reference can't be dependent on the load. So this voltage that we are getting, this is dependent on the load because here you have a resistive divider that is connected across this output, and over from here you are getting a the sensed voltage which is the attenuated version of the actual voltage, because there will be some attenuation, but this reference voltage, this this will be an independent quantity. This will not depend on the load voltage. So this is the one that will tell you that okay, you need to maintain this reference value. Whenever it fluctuates from this value, you need to maintain it. You need to make it again to this. You need to return to this value only, right? So it can't be dependent on the load voltage. Okay. So you see there is this. This is a shunt regulator basically. If you see the shunt regulator circuit, see there is this with the voltage, there is this series element and there is Zener diode. So the application of shunt regulator is to create these voltage references and current voltage references, right? So here if you see there, this is the same circuit. This is the source voltage, and then there is this series resistance, and then one Zener diode, right? So this is independent of this output voltage. You understood, right? So your reference shouldn't change. Your reference will be constant. This actual voltage will change, and you need to maintain the actual voltage as per your reference. Okay.
Okay, ma'am. And how feedback over here is helping.
Sorry.
And how feedback is helping here.
Can you write it? You are not audible. How this? What is helping what?
Feedback.
So unless you give the feedback, how will you know whether this value is getting maintained or not? So you will not monitor in actual systems. Things are not monitored manually, right? You can't really just okay, like all the time you can't really see okay now this voltage is this much that much. There are some automated systems. Now due to that, unless you give some feedback, okay now the voltage is this much, how will it take action? For your controller to take action, you will have to inform it, right? That okay now this is the voltage, this is not equal to the reference voltage, now you take action. That's why this feedback is required. Otherwise, how will the controller know what is happening in the output?
Okay, ma'am.
Okay, just a second. Just wait a minute. I will just connect the charger. Just a minute. Yeah. Okay. So next we studied the switched mode converters, right? After the DC-DC regulators, the switched mode converters came. Why? Because the linear regulators were not very efficient. So the efficiency was very poor. We can't use those things in high power systems. So that's why these switched mode converters were developed. So the most basic configurations are buck converter, boost converter, and buck boost converter. So here, so each contains one half bridge. Okay. So basically, the buck converter you can also draw like this. So in that case, you will see this contains a half bridge. Okay. So the configuration is something like this. Sorry, just a bit. This is just to show you that you can generalize these circuits. So they are just basically different combinations of inductor and switches. You just rearrange the inductors and switches, you will get the converter, a new converter. Okay. So like this, you have this half bridge like this, and from here you have this inductor, and then the capacitor and the load like this. So in question you they may give you the diagram like this, so don't get confused. So the you can also draw buck converter like this. Okay, like this. So this is one switch, and this could be a diode also. This could be another switch also. Okay, it may be a diode, it may be a switch also. If this is a controlled switch, then we call it synchronous buck converter like this. And boost converter also you can draw like a half bridge, like the switches, the configuration you can draw. So here you have the inductor in series with the input, and here you have the half bridge. Okay, here you have the half bridge like this, and then you have the load across the capacitor. So you understood, right? How I drew this? There, the connection is basically the same. I just drew it in a different manner. Okay. And another interesting thing is, so if you look at buck converter from this side, if you look at the buck converter, suppose sorry, uh, yeah. So if you look at the buck converter from this side, suppose this is the source side, then you see this becomes a boost converter. Suppose this is your input, then you have this capacitor. So usually in the input side there are some filters, but anyway, so you see there is this inductor, then there is this half bridge, and there is another source. So instead of that you can connect the load, so this becomes a boost converter. So buck converter and boost converter, they are the dual of each other. So if you see the from this side, this is the buck converter. If you see from this side, this is boost converter. Okay. And then there is buck boost converter, which is again consists of two switches, and you can also draw it in terms of a half bridge. Okay. So you can already see this is the half bridge, right? So this is the half bridge over here, like this. And the inductor is connected like this. So these are the three non-isolated DC-DC converters. All the other converters are derived from these three converters. Either the converter will be buck derived or boost derived or buck boost derived. Okay. So these are the most basic converters. Yeah. So after the non-isolated converters, we discussed the isolated converters. So the first isolated converter we studied was forward converter. This is a buck derived converter. So its operating principle is similar to a buck converter. The only difference is that now you have isolation. Now you have this high frequency isolation transformer. This is the extra thing. Otherwise, it operates in a similar way like a buck converter. So first, when this is the input voltage, so when this switch, suppose this is Q, so when Q is on, then the current will flow like this, and if the then the polarity, relative polarity will be this, then this diode will get forward biased and inductor will get energized. And just like buck converter, you see for buck converter also, when this switch was on, current will flow from the source through this inductor and through the load like this. So in a similar manner, the current flows in a way, and then when you turn off Q, then what happens is this diode is, you turn off Q, now current can't flow through this winding, right? Because now this path is open. Now the relative polarity gets changed opposite because you are interrupting the current. So now it needs some path to flow. That's why this diode and these resistances are given so that the current can free wheel over here. And now this diode will not conduct. The inductor current will free wheel through this diode, just like the buck converter. So this portion is exactly same as buck converter. The inductor, this diode, and the capacitor. Okay. So here the output voltage, input voltage relation is this. This extra n term, this comes because of the transformer. Otherwise, this is same as buck converter. Fine. So after forward converter, we studied the flyback converter. Flyback converter operates similar to a buck boost converter. This is derived from the buck boost converter. Buck boost converter. Derived. Okay. This is derived from buck boost. Here, here again you have this isolation, but the point to be noted here is that for forward converter, this was operating as a transformer. But here this is not operating as a transformer. This is a coupled inductor. Okay. Because for transformer, there is no energy storage. So if there is input in the primary, simultaneously you will get simultaneously the power will get transferred. The operating principle for inductor is what? So first it will store some energy and after that it will dissipate that energy. Okay. The energy storage and the energy dissipation, they don't occur simultaneously. But for transformer, the the input, the energy, like the energy is drawn from the input and simultaneously you are giving output. So there is no storage. Okay. Anyway, so yeah, so that you need to remember that this is not a transformer here. The operating principle is different, but we but it is giving isolation. That's what we require. We need the isolation. Yeah. So here again there is this switch. So the current flows like this when Q is on. But here you look at the polarity is like this. So when this terminal is positive, this one is positive. So current can't flow because the diode is forward biased now. But when you turn off Q, then current this diode gets forward biased. Why? Because now the polarity is opposite like this. Then the current will flow like this. Okay. So similar to a buck boost converter, first the inductor gets charged, and after that it provides to the load in the next interval. We also saw the timing diagrams, the flux waveform, the current through the switch, the diode current, then capacitor current, all these things we saw, right? This is the primary voltage. This is the voltage here, the voltage across the primary winding, VP. Okay. So this is also a very important and very popular converter, flyback converter. For low power applications, flyback converter is very popular. Okay. So yeah, I think this much only I will cover. The the last day closed loop controller part I will discuss because somebody mailed me that they wanted the explanation of the pulse width modulation. So I will explain that a bit. Okay. Otherwise, I haven't discussed here the inductor design and the transformer design part because they are very there are steps to follow. So I am not discussing it. If you have any particular query, you can mail me or you can uh, ask me. Okay. So yeah. So actually today I have not included any problems, but I have just these two problems I have taken. But I think you have all. I don't know whether you have already seen this in other tutorials because there are other TAs also. They may have already solved this one. But anyway, I will just discuss this. So this is the problem related to the inductive turn off of the BJT. Okay. The inductive turn off base drive circuit details are given below. What is the value of L required in the circuit? So why? So this is the multi-stage base drive circuit that we discussed for the BJT. Now, this inductor is connected. What is the purpose of this inductor? The purpose of this inductor is to accelerate to make the turn off process faster. So, in the base emitter junction of this BJT, some charges are stored. When you turn this off, so this charge needs to be removed. If there is an inductor here, then this charge removing process is faster and the turn off is also faster. If your turn off is faster, then the loss incurred in the BJT is also lower. That's why to get lower loss, we connect this inductor here. When the base drive we provide via this. So like this, we provide the base current. Okay, like this. Now when this turns off, so this current will be, so the current direction will have to be opposite so that the charge stored can be removed. So the current will flow like this. Current will flow like this through the inductor. Okay. So here what are the parameters given? VCC, IC. So IC means this one. I guess so. Uh, this current, this IC is given. Then VBQP. So the base emitter junction drop 0.7 volt. HFE sat, that is beta, is given 20. DIL by dt is given Then R2, R1 values is, it is given that I base is 1.5 times 2 IC by HFE set. Okay. So this is also given, right? Now, how will we proceed? So, can anyone of you can anyone of you tell how to proceed with this one? It is not necessary to tell the whole thing. You can just also tell what could be the first step, like this. Even if you don't know how to find the actual answer, but just say the step. What can be the first step to find? Okay, I haven't. Okay. So you see, I told you that when the BJT will turn off, then the current will flow in this fashion, right? In this fashion. Now, if you apply KVL in this loop, what will you find? Suppose we take the polarity across the inductor like this. So what will be the KVL? L by dt. So L di by dt. Then from here, so this is the base emitter drop. So minus VBE QP minus VBE QP. This is the switch QP. Then over here, again you have the drop across the resistance. That is R2. R2 times IB, right? R2 times IB. That will be your KVL equation. Now you see this di by dt value is already given. This is they have said that you can take 0.5 IC. So IC you know 5 ampere. So 0.5 IC. So this is known. Di by dt is known. VBE is known. That is 0.7. R2 is known. What is IB? IB is again given here, right? IB is also given. So HFE set is 20, IC is 5, and this is 3 times IC by HFE set. So you know all the quantities, right? Then you can find out what will be the L value, right? Can some of you calculate what will be the L value? Anyway, I think you can calculate later also. So you understood, right? What will be the process? So just apply KVL here and then you can find out what will be the L value. All the other things are provided here. Okay. So, and there is another question. So this is an isolated DC-DC converter, a coupled inductor in series with a MOSFET operating at 80 kilohertz with duty ratio varying from this to this. RCD turn-off snubber is connected in parallel to the switch. The input supply to the converter is 48 volt. Inductor current is 65 ampere. Snubber capacitor required if the maximum turn-off time is 16 nanosecond. Okay. Now we studied the snubber circuit. What is the requirement of a snubber circuit? When you turn off the switch, so there some LDI by dt will come here. Whenever you interrupt the current through an inductor, suddenly then LDI by dt voltage will be impressed across the inductor, and due to that, the voltage that the switch has to withstand, that becomes this supply voltage plus this LDI by dt, right? And if this exceeds the voltage rating of the switch, then the device will blow. In order to protect this device, we provide this additional circuit which is called the snubber circuit. So the inductor is there and current can have two paths from here and through here. So if you turn off this circuit, this switch, then current will flow through this diode and it will charge this capacitor. So now you are not interrupting the inductor current. The inductor current has additional path to flow. That's why the switch, the additional LDI by dt will not come across the switch and the switch will be fine. Okay. And the capacitor is charged during the turn off process, and when the device will have to turn on, then the capacitor will discharge through the resistor like this. The capacitor will discharge when you turn on this switch. Okay, so that will be an RC circuit. So these things we discussed in the I think in the gate driver portion only. So the current was initially like this, then the inductor current falls like this, and VCE, this voltage rises like this. So the current equation is equal, the IL is IC plus I capacitor. So this is I collector and this is I capacitor. And IL you can write like this because the current through the switch is falling. As you turn off the switch, the current will fall and we assume it a linear fall. So the equation we can write like this. So yeah. And again, what is the capacitor current? The capacitor current is IL T by TL, right? Because here IL will cancel. So I capacitor is equal to IL times T by TL. And what is VCE? The VCE voltage is this, this one, right? That will be the, because this, the switch, the potential across the switch is basically the voltage across the capacitor. So that is 1 by C integral IDT. So the potential across the switch is 1 by C integral IDT. And I cap expression, you can replace this one. You can replace this one. And this is the initial conditions. Then you will get this expression. Okay. You will get this expression. Now here you see they have given a range of duty 0.3 to 0.7, right? So they have given this duty range and they have also given that inductor average current is 65 ampere. Okay, this is 65 ampere. So I guess, yeah, so input voltage is also given. So you can find out what will be the ripple and what will be the maximum current through the inductor. And that current you can replace in the IL value, right? Because you need to account for the maximum current through the inductor. And TF value is also given, the fall time is given, VCC value is also given. Okay, VCC value is also given. So you can find out the capacitor value. So this is wrong actually. I think this will not be, I will just calculate. I think this will not, this is not the correct value. Is 6. So I think I have calculated this one, but actual process should be that you should take the peak current, right? You should take the peak inductor current. But anyway, I think there is no way you can find it out because enough data is not provided. There is no data provided about the output current or anything. So you will have to take this current only. Okay. So you will have to take this current only. Yeah. So the last thing that we will discuss is the sine pulse width modulation of the single phase inverter. Somebody asked me to explain it again. So there are two kinds of sinusoidal pulse width modulation. One is unipolar, another is bipolar. The general process is simple, very simple. You have one carrier wave of triangular shape, or it can also be sawtooth, and the frequency of this triangular wave is much higher than the frequency of your reference wave. So you see here, this is one complete cycle of the reference wave, but here already this triangular wave has completed 1, 2, 3, 4, 5 cycles, right? But actually it is even higher. Here, for the sake of understanding, I have given a zoomed version, but actually this frequency will be even higher, like more than 20 times like this. Okay. So, you have this kind of reference wave, which is a sine wave. That's why it is called sinusoidal pulse width modulation. Now, what is the logic? If your V reference is greater than V triangular, then the high side switch will get pulse. That means the Q1. Okay. Q1 will get pulse. Uh, so like this, right? So this is high. PWM-A. And similarly, when this is less, then it will be 0. These are the gate pulses. And the low side switch always be the complementary of the high side switch. If there is only one reference wave, then this is called bipolar SPWM. Why? Because in that case, whatever be the pulse of Q1, you will give the same pulse to Q4. And the pulses of Q2 and Q3 will be complementary to Q1 and Q4. Okay, this is called bipolar SPWM. Why this is called bipolar? Because in this kind of switching logic, the voltage across the load, suppose the voltage VAB, if you plot, you will see the voltage is either plus VCC or minus VCC. Okay, let's call this VDC. We will call this the DC link voltage VDC. So the voltage across the load will be either plus VDC or minus VDC. Okay, that's why this is called bipolar. So if we just plot it, so this is uh, PWM of Q1 as well as Q4. So when these two switches are on, you see that the voltage across the device, across the load is plus VDC, right? So it will be plus VDC, and the moment it changes to Q2 and Q3, the voltage switches to minus VDC. Okay, the voltage switches to minus VDC. Again, when Q1 and Q4 are on, then again it is plus VDC. Like this, the voltage goes. So it doesn't stay at zero level. It is either plus level or at minus level. Okay. So there is one disadvantage of bipolar SPWM, because you see the instantaneous difference of this square waves and the actual desired wave. This is very high because it is fluctuating between plus VTC and minus VTC. So you see the instantaneous difference is very high. So that's why it calls the harmonic distortion is more in bipolar SPWM. Okay. But in unipolar SPWM, we will see the harmonic distortion is less. You understood, right? How this bipolar SPWM? Okay, so now
Yes, ma'am.
if we go to unipolar SPWM, in that case we will see that there are two reference waves. One is like this that we already saw, and another one will be the one inverted sine wave. One
So we have,
inverted this, yes.
now I want to ask at the peak of triangular, why PWM of A is low?
Repeat once.
Ma'am, at the peak of triangular waveform, why PWM of A is low?
Because of this logic that I told you, right? When V reference is greater than V triangular, then only this pulse will be high. But in this region, you see this is the reference wave and this is the carrier wave. So the carrier wave value is higher than the reference wave. That's why this is low.
Okay, ma'am.
Hmm. Yeah. So for SPWM, you see there are two sine waves. One like this, another 180-degree phase shifted inverted sine. So here the advantage is you get zero levels in the load voltage. You get plus VDC, you also get zero level. In the you see in the positive half, if you want this kind of voltage, the average voltage, if you want like this, then the it is embedded here, right? It is embedded like this. So in the positive half, you only get 0 and plus BTC, and in the negative half, you get 0 and minus BTC. So the instantaneous difference is less from the actual output and the pulse width modulated output. So that's why the harmonic distortion is less for unipolar PWM. And you will net the filter size will also reduce because the harmonic content is less here. Okay. So the filter value basically will reduce. For the same, if you want the same attenuation for bipolar and unipolar, for bipolar you will have to use higher, more bigger filters. Okay. And what is the switching logic? The switching logic is same like this. So when V reference is V reference, suppose we call V reference 1 and V reference 2 because there are two sine waves. So when this is V reference 1 and the red one is V reference 2. So when V reference 1 is greater than V triangle, then then the pulse of Q1 will be high. Only Q1, not Q4. Only Q1, the pulse of Q1 will be high and Q2 pulse will be complementary to Q1. And when V reference 2 is greater than V triangular, in that case, so in that case, the pulse of Q3 will be high and Q4 will be complementary to Q3. Okay, this is the switching logic. So if you follow this logic, you will see this kind of waveforms you will see. This is A, this is Q1, this is Q1 complementary, this is Q3, and this is Q4, and this is VAB. Okay. So unipolar PWM is advantageous in terms of harmonic distortion, but this in terms of implementation, this is a bit complicated compared to bipolar because here you need two references and the pulses will be different, right? The pulses of Q1 and Q3 will be different. Yeah, so that's why this is a bit difficult for implementing compared to bipolar one. But this gives better performance. Okay. So this much only I had to discuss today. So yeah. So yeah, I think if you have any question, you ask. Otherwise, we shall conclude. Okay. Okay. So thank you for joining and all the best for your exams. I hope I could explain you because I don't know. Like I will also like if you give some feedback. I don't know like because this was my first time teaching something. So I don't know like whether I explained it properly or not. But anyway, like I shall try to improve, and I hope I could make you understand the concepts. Yeah,
Thank you, ma'am.
yeah. Thank you. Thank you for
Have a
joining.
nice day.
Thank you,
For
madam. This was very good, and yeah, you made our concepts very clear. So
yeah,
thank
yeah.
you so much.
Okay, okay, okay. I am glad that I could help you in a way. Yeah. Okay. Okay. All the
Thank
best.
you.
And yeah. Bye. Bye.